Hello, it's Professor Todd again. Let's take a look at a simple um, motor pumping circuit and how to implement it using standard logic gates. Okay. Okay. Um, so we are given that we have the inputs into our system. Okay, for this pumping system, whatever it's doing, is that there is a low level switch, and that's a low level switch right there. And we are going to assume that our input switches, excuse me, pardon me, the devices are designed so that it gives a logic 1 when the switch is active, which obviously means it's 0 when inactive. Okay, so once you know one state, you automatically have the other because there's only two. There's a high level switch, so it's logic 0 when enabled. So that means 1, it must be 1 when disabled. Hopefully you see that's fairly obvious. Motor overload protection, logic 1 when active, 0 when inactive. So normally a motor overload is there, to disconnect the motor from the line if it's, if there's a problem of some sort, either mechanical or electrical short, that it draws too much current. So whether it's an electronic overload or thermal or magnetic, then normally it's in its rest state. It lets current to pass, motor current to flow. So it's sort of that would be in its inactive state, and then in the event of an overload, it becomes active. Okay, and then there's this operating mode switch, and it's a logic 1 when it's off. So you will agree then in the on state it must be logic 0. So if you look at the control statement here, it says the sump pump motor will operate if the operating mode switch is in the on position. Okay, so the operating mode switch is MS, mode switch, and if its logic 1 is off, that means on must be logic 0. So that would be MS, like that. Okay, so that's for that bit. And the high level switch, I want to change my highlight color here to use green. And the high level switch is enabled. So then that would be then high level, which is HL. It's enabled, so it's logic 0. So HL is logic 0. So just to recheck it, so MS is on. Yeah. And HL is enabled. Yeah, okay. And then let me loop. And then the low level switch LL is inactive. So that's going to be this one here. If 1 is active, 0 is inactive, then this would be LL not. And finally, the I guess I'll go back to yellow. The motor overload OP. Oh, wrong tool. My apologies. And the motor overload OP is not active. So this would be O, P, and inactive would be logic 0 if one is active. Okay. All right. So then, therefore, we could say then our output PM or whatever you want to call it, doesn't matter, PM equals. So in order for the motor to run, this must be true. And this must be true. And this must be true. And so all of these statements, I just want to get rid of that, must be true in order for the motor to run. Okay? Now, I add a condition here that says when the motor is running, we'll get to this, right? So it means the logic gate output when it's low. So what that means is the output so a low output when running, and because of that we're going to put a bar across the whole thing. Now, so in order to solve that, that forces us to use De Morgan's theorem. Okay, so De Morgan's. And therefore what you do is you break the bar and change the sign from and to or to and. In this case it's going to be and to or. So that's then going to be M S anded and then whoops, sorry, that would be I didn't listen to my own statement. Or, and then that bar is broken down over each term. What's that? Sorry. And that means this double inverter cancels. So that's going to be MS plus okay, so that should be it. Okay, so then if all those cases are true, then that would be the statement. Now, if we wanted to have so the output was high when the motor's to be on, then we would not put this blue bar here, and therefore you could just simply leave it as it is. All right, so now this current syncing thing, so each logic gate family, is there anything else that I would like to add? No, I don't think so. Of course, if you wanted to, you could put it in the truth table, and I've done it. Put these two in the truth table, and see that you end up with the same response. So with these ones, right, a whole set of conditions needs to be true in order for the motor to come on. And if any one of those conditions is not met, the motor's not to be allowed to start. And I would assume that makes sense. So anyway, thanks for watching, and we will catch you later. All right, cheers. God bless. Bye. current and voltage specifications, and I have another video on these 74 LS series that covers all that, so I won't repeat it all right now. But current sinking's like depending on the gate. Now, it doesn't matter which type of gate it is, because the terms are all the same, and within the same logic family, the specifications are all the same. So I'm just using an AND gate as an example. So current sinking means is that current is flowing into the gate, and inside the gate here there's, I mean, this is simplified, but okay, there's a transistor there which is then saturated, so it pulls the output down to ground essentially, okay? And then this would go up to 5 volts, and this is the LED, okay? And this is for current limit. So current will flow down this way when this output is logic low through that internal transistor. So it's sinking the current. That's like water's being poured into the bucket. Current sourcing is the current goes the other way out of the gate, and that's like water's being poured into the bucket, if you will, as a memory aid. Now, in the 74 LS series, again, each logic gate series, and there's quite a few of them, they have their own unique specifications. The current sinking current, the maximum rated is 8 milliamps maximum. But for the sourcing current, in which case current is leaving the gate, it's only rated at 400 microamps, which is not enough to turn on an LED. So you want to use the LED for the current sinking. Now, if you put a transistor, BJT or MOSFET, in there, then you can do whatever you want. Then it's not a problem. But for the LS series, to switch an LED directly, this is the way you need to do it. So our diagram there is calling, like, this point here is PM. Okay. All right. So